Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Sloane Wiktorowicz and Agnieszka Słowikowska with us today. Hello,
Hi.
Sloane. Hello, Aga.
How's it going?
Hi.
And I apologize for any butchering of your Polish name. Sorry. Let's see. And Aga, where are you located at?
Now I'm in Groningen. I have just moved to Netherlands while I'm started to work in JAI. This is Joint Institute for VLBI. And I moved from Torun, from Poland.
Very good. Very cool. That's a very awesome telescope behind you there for a background image.
Yes, this is our radio telescope in Poland, which is 32 meters, and it's one of the European VLBI network station as well.
Beautiful, beautiful, very nice. And Sloane, where are you located at?
So I'm in the Los Angeles area. I work in LA area. So it's nice and cloudy and cool here for now.
Oh. Yeah, spring must be in the air somewhere around April. So I'm in Phoenix on this April 25th, 2023 as we record this, and we haven't quite hit summer yet. We're sort of in a late spring, so we're in the 90 Fs. So the power switch has not been hit yet, but it will be. So very good. And Sloane, what do you like to do for research?
So my main focus is extrasolar planets. I've been fascinated in them for a while, short, long period, all of those, variety of techniques. The last few years I've been getting focused into asteroids. There's a lot of cool physics.
Yeah.
It started off as calibration objects, but there's a lot of interesting stuff we can learn about them too. And they're a lot easier to detect than exoplanets. So know where the data are.
Indeed, indeed. And Aga, what do you like to do for research?
Mainly compact objects, white dwarfs and neutron stars, isolated or in the binary systems. And for the last years, I'm also very interested in polarimetry, in X-ray, well, in the radio and optical domain. And of course, there is now a huge interest in the X-ray polarimetry as well.
Indeed.
But yeah, I'm also driven for the instrumentation.
Very cool. Very cool. And that is going to bring us to this very awesome APJ supplement article. It's open access, people. We're in the dawn of the open access. You can go get a copy for free. Go grab one. A decade of linear and circular polarimetry with the Polish 2 polarimeter. And Sloane and Aga, take us away.
So thanks for having us here. I'd first like to acknowledge our co-authors here. So Aga's been with me for a bit. We've been working on a lot of different things over the years. You'll see a lot of the co-authors, actually, they were undergrads or postdocs at UC Santa Cruz back when we started this work. And they've all kind of moved on to different areas, but they all contributed to the data taking. They all got trained on the instrument. They all learned some of the instrumentation, helped debug things, write checklists. So it's really was a team effort to get the instrument built and operational. And it's cool that, there's so many different affiliations now because they've all sort of, moved on over the course of 10 years. There's a lot of folks from aerospace where I work, Aerospace Corporation. We're a federally funded research and development center like JPL. So we, have same sort of folks. So there's a lot of engineering support. I'd like to also call out Gary Cole in the middle. He's an amateur astronomer who's built his own instrumentation at home, and we've cross-calibrated observations throughout the years, and his data always line up pretty well. So we've been, on and off doing a lot of work together. So I'm happy to have him part of this work.
That was an awesome shout out to the students and Gary. Very cool. Good.
So this is a big paper. We might just start at the back all the way on figure 16, just to show some of the results, and then we'll try and explain a little how we get there. There's a lot of meat to this.
Let's start off with figure 16, and there we go.
So polarization, there are catalogs out in the literature for linear polarization of a lot of stars, and you can see they go from very, very low levels of polarization, a part per million, all the way up to 10% or so. It's hard to get much more than about that with stars in the interstellar medium. I'm just plotting the catalog values for certain stars versus what the Polish 2 polarimeter, which is the focus of this work, we developed the measurements that we've taken and how they correlate. And you can see, you know, there's low polarization, there's high polarization. A lot of these targets are variable, and that's one of the main results of the study, which a lot of literature studies have shown that everything that's polarized is also variable, essentially. So it's hard to find great calibrators.
Okay. Right.
And that's kind of the whole point of it. You know, the science targets are variable. The science targets have sensitivity to asymmetry, and that's what polarization helps you disentangle.
Right.
That means that the calibration objects also have their own unique variations.
Right.
So you're going to find things that don't match up. Sometimes there's typos in catalogs, but usually things are just variable. And a lot of objects that used to be good calibrators are no longer. So it's an evolving sort of story. So maybe we should head up
let me ask, what do the colors mean here?
So the colors and the legend are showing that depending on what instrument is being used to detect the measurements, we sort of tried to break them up into what's what. So for instance, work that my colleague Gary Cole, who has his own observatory, those are in stars. Got it. And so you can see there are two of them. Yeah, those two that are a little bit offset from the one-to-one line. Right. The catalog values that have been in the literature for 20 years or so of the same targets are above those. So HD 97991 and 18537. Right, way up here. Mm-hmm. This is just meant to show that things change, and the question is whether there was just something simple in the the previous catalog, or whether the objects are intrinsically variable. It's not completely clear. Yeah. But this highlights, if you look at a catalog and your values disagree, sometimes it's worth getting a third opinion. Absolutely. And in this case, the third opinion was pretty close to what we measured. But it was, this was one of my colleagues from home with his observatory, outside.
I think,
and he was able to take data that are very helpful to understanding is our Polish 2 instrument behaving properly or not. Yeah.
So where is it? Where is the Polish 2 instrument? Where is it?
So right now it's in the Aerospace campus in El Segundo, California, near the LA area. But these data were taken primarily at the Lick Observatory 3-meter and 1-meter telescopes near San Jose, California, Silicon Valley.
Mount Hamilton.
Mount Hamilton. So polarimetry is a great use for a facility like that. Whether you have light pollution or not doesn't really affect the polarization sensitivity, because it's an inherently differential technique. You're looking at the fraction of light that's polarized. And so if you've got contaminating sky issues, usually you can subtract them out pretty well. Okay.
And I think you can, look on this figure also in very global context. It's like gives you that people, they have been working on the catalogs, polarimetric standard catalogs for years, but the last decades, I think it's blooming and it speed ups, because first of all, we have more and more instruments that they perform observations on a regular basis. Therefore, you can detect exactly what Sloane was already mentioning, that some of the sources are variable, and of course, then it is not a good calibrator. And you can also see that this is really a very comprehensive and complementary work, because here we are providing the catalog values and measurements in UBV bands, cool. Whereas the other catalogs, they are in the in R band, for example, the RoboPol catalog. Yeah. So it's really complementary, and you also can see, I think, what is really cool is that this instrument can go to the ppm, and I think this is where the story starts. So about the instrument.
Nice sensitivity. Very good.
Another thing that I'll mention here is there are other instruments that can go to the ppm level, and we tend to agree for the most part. It's not exact, but it's nice to see that all of us are still congregating at similar values for both the high and low pole objects. So we think we're all doing it fairly well.
Good.
But also, this plot shows only the linear polarization, right? Mm-hmm. Which is also worth to mention that Polish 2 can measure all the stock. So I, Q, U, and V And it's not very often, especially, I mean, in the optical domain, right? I mean, there are many polarimeters that measure linear polarization.
Yeah.
There's a lot of spectral polarimeters. So of course, for the, checking the V to get the Zeeman effect and so on.
Mm-hmm.
But there's not many that can have such a dynamic range and the time resolution and measure all four of them. So I think it's really cool.
Very cool. So is the Polish 2, so is it in a working state right now? Is it?
It is. It is. Yeah, it is indeed.
Is it going to go back to look?
Well, so maybe this will sort of give a spoiler to the end of the talk, but there is a new instrument that are built called Phalanx that we took up to Lick Observatory and commissioned it in January 2023. So very recently. So still fleshing out the capabilities of that one, but the hope is to transition from Polish to Phalanx. It's got a better faint limit, which is helpful. So maybe we can move to the previous figure, 15.
Sure. That's good.
It goes to what Agua was mentioning about the circular polarization.
Yes.
So if you go through all the
lovely
data, you find a plot that shows how the circular polarization compares to the degree of linear polarization that we measure with this instrument. And as Agua mentioned, it's not that common that an instrument measures both, and certainly not at the same time. So you have instruments that use conventional wave plates, and you can usually swap out a wave plate for a wave plate and have the instrument sensitive to circular or linear. But in this case, we can do both, and we can explain that ad nauseum as interest is there. What's interesting is you can see how the circular polarization compares to linear polarization, and there tends to be some sort of clumps, and a lot of that seems to be related to interstellar medium, where the interstellar medium, because of extinction, causes linear polarization, and the bottom trend there, the 0.01 times p line, that shows what has been proposed in the literature by theorists for 50 years or so, that you have about a 1% efficiency converting linear polarization to circular. If you've got the right grain alignment and grain size variations and grain rotations along the line of sight, you can generate circular polarization. And we see that. And that's been known again since the 70s that some of these strongly linearly polarized objects also have circular. So we're seeing some of that as well. There are some objects, though, that just sort of stick out.
Yes.
Probably the best known one is, right there. It's a magnetic white dwarf, GRW plus 708247, been known since, I believe, the 70s. It's got a very strong circular polarization. It's percent level circular polarization in broadband. And that's just not, that's typically just not there. The only other object we can find that comes close is VY Cima Canis Majoris, which is about 1% or 0.5% circular polarization. It is on this figure. Yeah, it's somewhere over there. Maybe on the right side it shows better.
Yeah.
So
okay, let's go over
that's sort of important because when you're trying, circular polarization has always been hard, and it's always something that's difficult to measure accurately and to really give confidence that one is measuring it accurately, because there's a lot of instrumental systematic effects that cause circular polarization. You need grain alignments that are quite exquisite to give you detectable circular polarization on the sky. All you need is a lens. All you need is a off-axis reflection in the lab. All you need is something in the optical bench that can give you circular polarization, and then completely hose your understanding. You think you have some new physics you've discovered, and it turns out to just be a systematic effect. So it's important to have these sort of calibrators on the sky, and there's not many of them. GRW is a great one, but it's at like plus 71 dec, so southern hemisphere can't ever see it. So VY Cima is definitely a good one. But in any case, we're seeing detections of circular polarization that seem statistically significant, that it's likely to be ISM, but there's not a lot of them. It's really interesting when you find one.
Very nice.
And, when you look at this plot, on the y-axis, check the line when you have 1%. So you have only 2 targets that have higher polarization. Yes.
Yes.
Circular polarization, 2. And, so think, that you want to calibrate your instrument and you have to have, the calibrators spread on the sky all over, along the right ascension, right? So you can really pick up one when you are observing your target. And you have two. So we are for sure, we are lacking the circular polarized standards.
Right. So what do you do with that right now? Or am I leading?
So the main thrust that we've been looking into is with Aga and me has been the crab pulsar, because it's been known since discovery that the crab pulsar has linear polarization variations within the pulse, between the main pulse, interpulse, all of that. There's a very well-defined trend in linear polarization. Circular, the story's a little unclear, and a bunch of us are trying to measure what exactly is happening in circular polarization. It gives you a handle on synchrotron versus curvature radiation. There's some interesting physics. You want to see the circular polarization from the crab. It's a little tricky though. So having the calibrators is really important.
Yes.
Indeed. And recently we just measured a few stars that are in the direction of the crab pulsar to be able to subtract accurately the component that is coming from interstellar medium.
Right.
So this is like on the level of 2%, but we also do it multi-wavelength, so to be able to subtract them in the given colors.
Yes. Very cool. Okay. What would you like to cover next?
Well, how do we get there is probably a good question. So maybe let's go to figure 1. I think that's the instrument figure. So this is fundamentally a different setup from what most polarimeters use. Most use a rotating half wave plate to get linear polarization. This is actually using, up at the top, you'll see PEM. That's photoelastic modulator. It's a bar of fused silica about this big.
Okay.
That's been known since the late 60s by James Kemp. He sort of used this effect for astronomy. It's a fused silica bar that when you hit it with a piezo and you ring it, it'll oscillate at 40, 50, whatever, kilohertz, 20 kilohertz, depending on the size of the bar.
Okay.
What that does is when it's vibrating, that imparts stress by refringence into the bar of fused silica. So it's like if you've got, a pair of polarized sunglasses looking at another pair and you rotate them, you'll see a bunch of weird structure.
Yes.
The stress field in the annealing process, or how the lens is held in the frames. You can imagine if that stress came and went, you would see bright and dark regions, as you're looking through at a light source or whatever. And you can use that to impart a known signal. This is the same way infrared chopping worked back in the day, where you look at an object and you impart a known variation, and you demodulate out that known variation so that you can then recover very high accuracy, very linear degree of that effect.
Cool.
So with the infrared, it was to detect objects from the ground in the presence of Earth's thermal environment. But with these photoelastic modulators, it's a way of looking at very low polarizations, part per million polarizations. And the goal of that is to detect scattered light from close-in exoplanets. So Jupiters from the 90s that we still don't know what's in their atmosphere, that you really need JWST to look at. You can also look at with polarimetry, and the hope is that as the star is blasting you with photons and the planet is orbiting, you can see the small change in reflected light as that vector rotates.
Cool.
And that small change is further discriminated into what the constituents in the atmosphere are. So the poster child for this is Leo back in the 20s. He built a polarimeter, and then he looked at Venus, and he looked at everything in the solar system, and he acquired the data that proved in the 70s that Venus has sulfuric acid clouds.
Nice.
So 20s instrumentation, and he discovered, people thought, oh, is there water? Are there, possibly life on Venus? No, sulfuric acid. It's a little different. So you can do that with exoplanets, and the hope is to be able to measure what their clouds are made of, because a lot of exoplanets, maybe half or so of close-in exoplanets, have clouds, and they're not all the same.
Interesting. Very cool. I didn't appreciate that you could get that with polarization.
That's the hope. So we're working on that. That's maybe the next paper. I'm working on the next paper. But okay. Yes, that's the plan, is to be able to do this for exoplanets.
Nice.
Because it's hard to do with a lot of other techniques. So JWST is going to be great. So the instrument then, once you have these photoelastic modulators, you kind of just have to put in the right pieces in order to get the light out. So what we're doing is we're converting incident polarization into time variable changes in intensity on the detectors.
Yes.
So it's an AC coupled measurement because there's not a lot of detectors out there that are sensitive intrinsically to polarization. You know, you've got a CMOS camera that's the key to your spectrograph or whatever. It's not really polarization sensitive.
Yeah.
You have to do something. You have to modulate the light. You have to change the polarization into an intensity variation, and then that gives you encodes the polarization information.
Okay.
So there's this Wollaston prism. It's just a polarizing beam splitter. What that does is it isolates that modulation and turns it into intensity variations. And then you've got a bunch of standard optical bench stuff, neutral density filters if you need them, some imaging. The detectors are different though. We're not using imaging detectors. We're not using CCDs or CMOS because it's a spatially unresolved instrument. So the goal is to trade spatial and spectral resolution for polarization sensitivity. You have seeing disk, you have aperture integrated, old style astronomy, where you're recovering all the photons, but you're splitting it very sensitively in polarization state. And so in order to handle and detect this modulation from these PEM photoelastic modulators, again, they operate at 50 kilohertz or so.
Okay.
The refresh rate higher than that. And so we're just using photomultiplier tubes.
PMTs.
19th technology. The Japanese have pretty much perfected them. They are, quantum efficiencies maybe 30%, but star, that's not too big a deal. It obviates the flat fielding issues that you'd have with like a CCD or a CMOS, because with the multi-pixel sensor, you're not, we don't need the spatial resolution. We're not going to see the exoplanet.
Yeah.
We just throw all the light on one pixel essentially. And then there's some guide optics there to make sure that we're on target. That's about it.
Yeah, but it's also, photomultipliers, the advantage is that, the dynamical range is great, right? You can measure Venus and you can measure the Crab pulsar, so more than 20 Mach.
Right.
And this is really cool. And also the time resolution that you can get. Right. Polarimetry is a photon hungry technique, right? So for the accuracy of 10 to minus 6, you need like 10 to 12 photons, right?
Okay.
Because it's like go 1 over square root of n.
Yes.
So this is just like really great to have the PMTs.
Right.
It's great to see PMTs still in action. Very cool.
When I built the first version in 06, this is the second version, Polish 2. When I built the first version, it was sort of like, okay, so you're trying to build this thing. You start with a CCD because that's what we had back then. Sure. But then that drives so many things. If you start with the detector, then you have to make choices in the instrumentation, and you start going off in a rabbit hole, and then your calibration becomes a nightmare. So the plan was start from scratch, look at the literature. What's the real goal? The goal, as August said, 10 to the 12 photons. So you want a 3 to 5 meter telescope looking at a fairly bright target for exoplanets. Yes. And this is the right instrumentation to do that particular job. It's not going to get you certain things that you may be used to, spatial spectral resolution, but it does get you the polarization sensitivity.
Very cool. Nice.
And with the CCDs, you get saturated so quickly for the bright targets. You cannot do it. No way, right?
Right. Right. Very nice. Very good. All right.
So maybe a little bit about the instrument is helpful. It's basically a visible light bandpass. We have the capability to go, different bands, UVV, R, pull out the filter and have a clear bandpass if you really are photon hungry, like for the Crab pulsar measurements. So let's go ahead and go down.
Okay. We'll go down.
So in this case, we kind of had to invent how to calibrate, how to reduce the data. There are similar instruments in the literature. Planet Pol was kind of the original one, built in, I think, 05. Okay. And then you have the hippie polarimeters that astronomers have built, and they've miniaturized them and made them a lot more accessible and 3D printed them. And it's a great way of getting great data on bright targets. With small telescopes. So we had to sort of figure out, you can't just take regular Python routines and reduce these data. You have to sort of understand the data first. So, bandpass on the left, figure 2. Figure 3 shows kind of the whole point of why this instrument is the way it is and why it is high accuracy. So you can, these are data from, I think, 2014, where you can have, when you're staring at clouds and the dome is closed because it's actually raining, you can just look at lamplight. And this is essentially what a flat field lamp looks like in instrument. So it's not imaging, remember, it's not really spectral resolution. Here's an FFT of just the raw data output. So again, you've got these bars of fused silica that are vibrating at 50 kilohertz, and you're measuring with your PMTs what the one-dimensional voltage output is. And you can see 60 hertz noise from the lamp, mostly 120 hertz. It's flickering. Yep. Lamps, when they've got a dimmer switch, which flat field lamps usually do, they have this triac circuit that ends up causing all of these harmonics.
Yeah.
You can look at the power grid, US power grid there, that's the 120 hertz, but you then have 1/f decay all the way down to kilohertz or so. So you can see the light flickering at those high frequencies, but then it dies off. Then it's gone. And then all of a sudden at 10 to the 4, 10 kilohertz, you see this spike. And you see a bunch of other spikes. It's kind of like spectroscopy where you're looking for H alpha, H beta at certain wavelengths. And when you see it, you've detected it, and you can detect red shifts based on the differences between where it should be and where it really is. We're kind of doing something similar here with polarimetry. We know we're imparting polarization. You can do the math. You can figure out if you've got a 50 kilohertz PEM that's oriented this way and a 41 that's oriented at 45 degrees, you can get, as August said, Stokes IQ, U, and V, linear polarization, both linear polarization states and circular. And we know where they should show up. And we know that at 10 and 90 kilohertz, you should see the Stokes U, this weird 45-degree polarization, linear polarization peak. At 100 kilohertz, you see Q, which is the vertical and horizontal stuff. And then 50 kilohertz is where circular is, and you don't see it here. So the lamp is really circularly polarized, but you do see other targets, the daytime sky for one. So all of those peaks that are higher than 10 kilohertz, all of those encode linear combinations of the beat frequency of, you've got, this thing going at 50 kilohertz, and this is 40 kilohertz, and there's all that spray at different frequencies, and those are all real. So use that to, what we do then is, when you're looking at a star, you know exactly where you're looking. You know exactly how this modulator is being used. You're hitting at it exactly 50.002 kilohertz or whatever, and you can use that particular frequency to multiply to do a matched filter essentially for your unknown data to recover exactly how much polarization occurs at that. There's a lot of old school technology here. This is called a loss amplifier approach. It's AC coupled. It's not something we typically do that much anymore in astronomy, but it works. It works pretty well for this particular purpose.
Awesome. Very cool. Very cool.
And this all amplification are done on the software base, right? And not the hardware, which is also great, because then, we store raw data. It's a huge amount of data, but then you can basically work on them in whatever approach you want.
Right. So these data, on a long winter's night, you can get about 500 gigabytes of raw data from Polish. Phalanx is 2 terabytes. It's a lot of data. Like August said, we're living in a great age here where computers are cheap, hard drives are cheap. It's actually a really interesting thing that the cost of hard drives is cheaper than the cost of the dorm room at the observatory. So 500 gigabytes versus a night at the dorm. it's cheaper. Just buy a bunch of hard drives. It's not that bad anymore. Wow. I've re-reduced these data, a dozen or so times as I learn a little bit more about how to squeeze more signal to noise out of the data. So it's nice to have the raw archive. Drives are cheap, and it's worth it. The cost of telescope time is definitely makes it worth it to just hold on to the old data.
Absolutely. You don't want to decimate the data
exactly
to save time, because then you can't go back and do another calibration or something.
That's right.
Perfect.
And as old school says, 90% of the time for calibration, right? But however, none of us want to do it.
Right.
That's right.
Yep.
Yes, indeed. So there's quite a bit of calibration in here. There's a lot of detail on how it's done, but the upshot is you want to use lab. You want to do it in the lab. You really want to do it in the lab, but it's really hard with polarimetry. It's with spectroscopy, or you're trying to develop your high contrast imaging test bed. You do it in the lab. You figure out all the, if you can solve it in the lab, then you can transition it to on sky and see what new challenges await you. But with polarimetry, it's so hard to get the right. It's so hard to know exactly what you're injecting. That's kind of the point. The whole point of calibration is you put a known source in, you measure what you get, you apply gain tables or whatever to get it so that you can look at an unknown target and have confidence that you're measuring, that you can trust your error bars.
Yes.
But if you think that a bare light bulb is 0% polarized, you're going to be mistaken, because anytime there's any kind of reflection, any type of scattering, it's the whole point of polarimetry, is to be sensitive to scattering and astrophysical phenomena.
Right.
Means that when you've got a light bulb in the lab and you're trying to focus it onto your detector, you end up imparting things that you don't really expect.
Yes.
So, middle of the paper kind of describes some interesting, funny stuff we see in kind of long held to be stable objects. So you really need to do it on sky. I mean, if you really, you really need to be able to look at objects on the sky in order to get good polarization calibration. And so you have a chicken and egg problem of somebody had to measure it.
Yeah.
Somebody had to measure it, and a catalog is only as good as the assumptions in the catalog. And so, you have to measure a bunch of stars and hope that on average things are nice. And so that's kind of the approach we've been taking. So we have lab data, but really it's the on sky. Yeah, go ahead.
Yeah, I was just saying that we can show the figure 4 where we have the lab data.
Right. Figure 4 is a good one.
Figure 4.
So
yes. Okay.
The thrust of this is not just to measure linear, but it's to measure circular polarization. And it's hard to calibrate linear polarization to high degree in the lab, and it's even harder to do with circular. So there's a few types of optics that you can use. And if you use a bunch of different things, you kind of can converge on a rough sense of what's going on. So here we have linear polarizer in a quarter wave. It's not a wave plate, it's a Fresnel rhomb. It's one of the most well-behaved circular polarizing optics in terms of wavelength, because typically one would use a super achromatic quarter wave plate, which is generally got roughly constant retardance as a function of wavelengths. Okay. But the problem is that there are ripples, there's a coating, there's always some asymmetry in how things are deposited, and you end up with a wavelength dependent effect. So if you really want to be able to get UBV, polarization that's accurate, then super achromatic may not be the right choice for such high sensitivity. We want really high accuracy, so we want to go for the best, and that tends to be our Fresnel rhomb, because it utilizes total internal reflection, which is a lot less wave dependent than a coating in a super achromatic wave plate. So a lot of instrument papers will show the sort of Malus law of you rotate the linear polarizer and you see the change in polarization. Well, here you may notice that the peaks are actually in Q and V. So Q is of the linear polarization states, V is circular. So here's actually modulation of incident circular polarization. When you have this circular polarizing setup and you rotate the linear polarizer in the system. So this is, there's a line there. That's a very simple model. A lot of the math is fairly straightforward. It's just sinusoids essentially, and the data line up fairly well with the expectation here. So that's good. But if you subtracted those, you would see residuals at a level that's much higher than what you would expect for exoplanets. For exoplanets, you need a part per million, 10 parts per million sensitivity. That's basically what you need. And the deviations here are going to be more than that.
Much bigger than that. They're visual here. So
right. So the main issue with getting the circular polarization accuracy is the instrumental conversion of linear to circular polarization. So just like aligned dust grains in the ISM can take linear polarization, and a little bit of phase retardance in the material will give you some circular polarization. We have that even with Polish, which is sort of the most it's sort of it should be the best linear to circular conversion environment that one can get. Theoretically, what you want to do is you want to put your polarizing optics as close to the secondary mirror of the telescope as possible. Close meaning in terms of the next optic should be the polarizing optic.
Yeah.
So a lot of polarimeters, they're kind of added on, because of the choice of the detector, because of the choice of it's got to be a spectrograph or an adaptive optics instrument or whatever, you end up with the polarizer. The polarizing optics are downstream of a lot of stuff.
Yeah.
And that stuff always messes with the polarization state. Since this was supposed to be a polarimeter first and foremost,
good,
not imaging, not spectroscopy, you have the polarizing optics first. That's why in figure 1, you had those PEMs
those two
right at the top.
Right.
Light from the primary mirror, secondary mirror, polarizing optics. No Naismith platform, no off-axis reflections. It's really to try and have the most pristine polarization environment where the telescope contributes as little as possible, the instrument contributes as little as possible.
Yeah.
And even then, those are the dominant systematic effects. You still have the telescope, you still have the instrument being some issues. So we can calibrate the circular polarization of the instrument. You can see it on figure 6. So in order to do a lot of this stuff, we came up with a bunch of kind of wild, kind of random experiments. One of the nice things about the Lick 3 telescope is you have some latitude to just try some stuff. And we take daytime data all the time. It's not always twilight. Sometimes during the day. I mean, there's measurements we took that are similar to this with Gemini North that were about noon, because I mean, you wanted to take the data then.
Yes.
So this, we just look at the daytime sky, and the Lick 3-meter telescope has a Cassegrain derotator because this Polish instrument is at cast focus. You really want, as symmetric a system as possible. So there was no prime focus way of doing this, so we had to go to Cassegrain. So the sky is strongly linearly polarized. That's why polarized sunglasses work. You can go outside and you can see that the sky gets brighter and darker as you rotate. So you just look at a patch of sky and you see the curve at the top. You've got Stokes Q and U as a function of theta, where theta is that orientation. Bit of a cheat because Q and U and theta are correlated. It's, there's an arctangent in there. So it's going to be a perfectly sinusoidal curve right there. And you see that when Q is maximum, U is 0. When U is maximum, Q is 0. That's how, you've got two basis functions of a vector and they're swapping.
Yeah.
The interesting one, I'd say, is the middle one, which is circular polarization. And you can see the blue data, first of all, the scale is a factor of 100 lower. So instead of 50%, we're at 0.5%. But we still see circular polarization. And it's not exactly lined up with the peaks in Q. It's not exactly lined up with the peaks in Stokes U, but you see that it's sinusoidal.
Okay.
The whole point of circular polarization is that it's invariant under rotation. If you have what you think is a real circular polarization source and you rotate your instrument and it changes, not from the, it's not real. It's a systematic effect. So this was a great learning experience because we're doing some circular polarization measurements for the Crab pulsar, for asteroids, etc., and trying to compare to the literature and understand how to do this properly. And we found that, that's absolutely a smoking gun for linear to circular conversion in the instrument.
Right.
What's interesting is this is actually lower than what you'd get with a conventional polarimeter. So it's kind of like, we see it clear as day here. And so with a conventional polarimeter with the wave plate, you have, you see it as well. But the saving grace here is since we can measure it simultaneously, we don't have to swap out optics and then have to figure out how to cross-calibrate the two optics.
Right.
Circular polarizing wave plate and the linear polarizing wave plate. We do it all with these photoelastic modulators.
Cool.
So you just gather all the data. You get the IQ-UV, and you can invert them and basically correlate and correct them out. So the pre and post correction data are shown in that middle plot, where the red is showing that, we fit for this. We kind of understand the physical cause of it, and we can correct for it. And the residuals go down another order of magnitude. So you're at,
very cool.
a few hundred parts per million. And that's in circular polarization. So what that means is we know exactly what in the instrument is causing it. So let's do some math here.
Yeah.
I think it's time. Let's go to figure
Showing
15.
the Milan matrix, right?
Right?
Yeah. Oh, which is there?
Figure 15, or I'm sorry, equation 15 on page 8.
Mm-hmm.
Yeah. So you can describe any optic, anything, whatever, an atmosphere, any kind of scattering process in terms of a Miller matrix.
Mm-hmm.
You can do Jones matrices, but I just use Miller because Miller, you don't have to have 100%, and just
it works.
That's just what I learned. So you have this 4x4 matrix of all the combinations of how Stokes I, Q, U, and V can get modified. So incident IQU V becomes measured IQU V, and there's all those combinations of what can do what to whom.
Yes.
And so part of the exercise here with calibration is to figure out what are the most important components, because you don't want to over constrain the fit. You want to just let the dominant processes speak for themselves and correct for those.
Okay.
As you're chasing your tail. So it turns out that measured circular polarization, it really requires only a couple terms. It's equation 16. It shows this M42 and M43. So that you can see in the matrix 42 and 43. So the bottom row means, so you start with IQUV as a column vector on the right.
Okay.
And you propagate it with this 4x4 matrix. And what you end up with is at the bottom row, so the M4, 1, 2, 3, 4.
Yeah.
That's telling you what the output circular polarization is. And it's telling you that it's dependent on the incident, Stokes Q and U. So the instrument really is taking Stokes Q and it's modifying it a little bit. It's taking incident Stokes U, it's modifying it a little bit. I have no idea why it shouldn't be doing this, but it's doing it. So there's maybe some residual stress in the photoelastic modulators that really shouldn't be there. In any case, it's fairly stable, and we can correct for it at a pretty decent level.
Cool.
So basically, this is what is showing the crosstalk between the Q and U to V, and this you figure out measuring the daylight, ray light, scattered light from the sky. Right?
Okay.
Well, it was shown in the figure 6.
Right.
Exactly.
Okay.
So there were measurements back in the 70s or so that show that the sky is also intrinsically circularly polarized at certain times of day. For this particular measurement, we measured that the intrinsic circular of polarization of the sky is pretty much 0. It's 28 parts per million with a error bar comparable to that. But that's this particular pointing at this particular site at this particular time.
Yes.
The atmosphere is variable. We know there's aerosols in the atmosphere and they're variable and all that. So at this time, what the better point is to measure that is to know that we calibrated to the accuracy level necessary to say that we don't think the sky at this time was circularly polarized at the 12 parts per million level. So that's doing okay.
Yeah.
So we hope that when we look at a star or an asteroid, that it's also not going to be contaminated.
Cool.
Worse than that.
I want to take a look at our final M. So we talked about that, and there's our incident, and then there we go. 17D is our final M.
Yeah, so that's the final M. So that's the extent to which Polish will contaminate the incident linear and circular, or mostly linear to circular conversion. And the order of magnitude there is 1%. So what that means is if you've got 100% polarized 100% linearly polarized light entering Polish, multiply that by 0.01, and that's the magnitude of the circular polarization contamination.
Okay.
So 1/100th. And that sounds really bad. Oh my God, if you look at 100% polarized sky, you're going to get a 1% circular problem. But most objects in astronomy are not that linearly polarized. An exoplanet host star is maybe 0.1% polarized.
Okay.
So divide that by 100, and then circular polarization is
even
you're ending up getting to accuracy levels that are competitive with the actual intrinsic effect.
Right.
So it turns out to be not bad. Also, this is the static correction. There's going to be an uncertainty on that 0.04, but it's going to be smaller. So you can correct for it, and the residuals again are maybe an order of magnitude or a factor of whatever, 5 lower. So you're not doing that bad.
Oh, very nice. Okay. Anything else you want?
So we
I
can,
think that it would be nice to also talk about the self-calibration, because this is really nice piece of work that the others can use.
okay, yeah, let's go down to
Is it figure 9?
figure 9. Yeah,
With
figure 9.
Gemini
So,
data?
yeah, so
Figure
so
nine.
for exoplanet, yeah, figure 9. Yeah,
Oh,
there
yeah.
you go. So for exoplanet science, you really need 1 to 10 parts per million accuracy, and that means you need a big telescope. And you always run into an issue where, if you're looking at a hot Jupiter, you're trying to get its atmosphere, you'd really like to do a hot Earth or a super Neptune, but they're too small for now. Let's just focus on the big ones.
Big
You
L.
still need 10 parts per million accuracy or so.
Yes.
So they have a few day period or a 1 day period or something like that. So you really want to order a week of time on an 8 to 10 meter class telescope, and that's expensive. It's doable, but it's expensive. And again, you then have these calibration requirements that you levy. So I'll get on the soapbox a little bit here to show that, when you're doing exoplanet transit measurements, you need to calibrate before the transit and after the transit, and then you're kind of done for, till next time. And that's usually a few hours, and that's a lot of telescope time. But here we're talking about full phase measurements. We're trying to see the exoplanet at all phases. Transiting planet, you want to see it at all phases. So you need to basically be on the telescope getting data all week and calibrate it every hour of every night for an entire. So you could spend all your time calibrating.
Yes.
Get any science, and you have that classic issue of how much time do you spend calibrating. So this technique actually is something that's been in the literature a bit, but I really want to bring it to the attention here that for an AAS telescope, you take advantage of the fact that something's going to rotate with respect to something else. There's no way to do it with an AAS telescope. You're going to have the field rotation.
Yeah,
you're going to have the, you can lock the Cassegrain derotator down, or you can let it spin. But in any case, either the mirror is going to rotate with respect to your sensor, or the star. You're going to have the stellar polarization varying, or you're going to have the telescope.
Yeah.
So we didn't mention it, but briefly, the dominant systematic effect is the fact that even at CAS focus, the telescope has reflectivity variations and imparts, 100 to 1,000 parts per million of polarization. So 0.01
from that,
1% polarization.
Swamps
and exoplanets, 10 to 100 times stronger than the exoplanet.
Yeah.
So what we can do is we can let the telescope polarization rotate with parallactic angle. So you turn on the Cassegrain derotator and keep the star, north up on the instrument essentially, and then that telescope polarization vector is going to rotate.
Yes.
So you measure it, and you can see that regardless of the polarization, the incident polarization of the star, the telescope has about the same effect. If on the left half, Q and U, you can look at the unpolarized HR 8585, bright unpolarized star.
Yep.
Polarized target HD 204827, it's about 5% polarized. You can see it's the red one, offset. Yes. And then you've got some exoplanet hosts, 733 and WASP 12. Right. So the vertical offset tells you what the intrinsic polarization of the star is due to the interstellar medium generally. But the variation, the sinusoidal variation with parallactic angle, is all due to the same mirror. It's due to the,
I'm with you.
Here it's Gemini North, so you got the primary and secondary mirrors. So when you subtract off that stellar polarization, you see on the right side, delta Q, that shows you that regardless of what star you're looking at, you kind of recover a similar telescope polarization.
Yeah.
What that means is, if you have enough data and you design your experiment properly, you don't have to calibrate on calibrator stars. You can spend your whole time on your science target.
Cool.
And you can use it to self-calibrate out the telescope.
Yeah, right.
And that's what we did.
Yeah.
What's that?
Apart from the fact that we also have to measure the sky background, but we will come to that later. Yeah.
That's true. You got to measure the sky background, especially when the moon's up. Especially when it's 90 degrees away in the plane of the sky, you then have you have nearly 100% polarized sky. So yes, you have to nod the telescope. There are other ways to do it. There's another group that has a much more exquisite way of doing this, but no matter how you do it, you end up losing efficiency. You lose a factor of 2 or so by calibrating the sky background. Is really not a great way that we know of to do that.
Right.
other than spending some time on the sky calibration. But yes, as Aga mentioned, you
Very
stare
cool.
at your science target all night, and it seems to work well. And I hope the next
Awesome.
paper that we talk about is a detection that I'm working on.
Yeah.
So
you
this,
know, we have, you know, there is instrumental polarization, like telescope polarization. There is sky background, of course, we need to take care. And then we also were checking what is the dependence of the polarization as a function of wavelength for both telescopes. And this is basically shown in figure 11 and 12.
11 and 12. Let's go down to 11.
Yeah. But I don't know, maybe Sloane wants to also discuss this dome experiment. However, yeah, I don't know. How
11 and 12 is great. So this is isolating what Aga was mentioning, that even at cast focus, any telescope mirror is going to have some intrinsic polarization. It's kind of an unavoidable consequence. You know, you're hoping that the mirror is all uniform and that pairs of rays from different parts of the mirror will cancel out, but a little bit of reflectivity loss in one is going to cause the other patch, because every patch is polarized and they don't necessarily cancel out.
Right.
And pretty much any telescope you go to is about 100 parts per million. Some of them are down to 10.
Nice.
Some of them are up to 1,000, but it's about 100 parts per million, and it's wavelength dependent. As like I mentioned, the lower the wavelength, typically the stronger the polarization. And so we look at a bunch of ideally unpolarized stars. You don't know if they're truly unpolarized, so you look at a bunch of them and look for outliers, and the core tends to line up with, you know, an average value of about 100 parts per million.
Yeah, around
3 meter.
Yeah.
And then figure 12 is like 1 meter, and you can do this for any telescope.
Yeah.
And it's usually fairly stable, actually, which is
that's good.
It's good.
Yes, it is.
So the variations you see are likely to be intrinsic.
Yes.
The star itself has a slight variation, but in aggregate, we looked at these data. I used to think that, you know, every night the telescope was variable, and I assumed that it was, and so I calibrated with that methodology. This paper reassesses that and finds that actually from one run to the next, from 1 week to the next, the telescope is not variable at a measurable level, and so that's helpful.
Very.
You know, if you're observing and you need to observe the same 3 or so unpolarized stars every night, and you get hosed by clouds and you miss one of them, what does that mean? How do you properly, you know, put those stars together in aggregate? So that was always the head scratcher. But as long as the telescope isn't really variable on the course of one run, it doesn't really matter.
Nice. Very nice.
It's been a very positive paper.
Yes, it's a happy paper.
Things aren't as bad as they could be. You know, even a dirty telescope with strong polarization, if it's alt-az, you can use it to self-calibrate pretty much anything. Variability isn't that strong in the telescope, so there's a lot of good lessons here.
Nice. A decade's worth of lessons. Very good.
Decade's worth of lessons. So maybe the last calibration thing to talk about is this dome shadow experiment, because it is kind of fun.
Dome shadow polarization.
Figure 13 and 14. So nobody would ever think to have your dome not aligned with your telescope, right? I mean, you're going to slew to a target, and your dome is supposed to be out of the way. But you can make it so it's not out of the way. On the left, we actually let the dome be static and track the star as it shadowed as it went into behind the dome, and you actually get a slow motion shadow sweeping across the mirror.
Yeah.
And what that does is it actually changes the polarization, because, you know, the telescope mirror, every part of it's polarized, and you're assuming that it all is going to cancel out. But if you shadow half of it, it's not. And so these are the data to show that.
Nice.
And so what's helpful about this is, you know, you measure the telescope to be about 100 parts per million polarized on the aggregate of what you think are unpolarized stars. Well, this shows that when you shadow the mirror, you get about 100 parts per million polarization.
Yes.
The upper right, the upper right Stokes Q is mostly where the effect is, but the lower left degree of polarization, P, 100 or so parts per million.
Yes.
It shows that, we are measuring what we think we're measuring.
Nice.
It's a 3 meter telescope. you wouldn't really want to spend that much time on an 8 meter on Gemini, but again, you can mess around sometimes. When you're slewing to the target, usually the dome is the slowest thing. You know, these big fat domes are usually pretty slow.
Takes a little while.
So what we did is, if you go to figure 14, we slewed to a target calibrator, bright calibrator star, and just started taking data, even though the dome wasn't ready. And you could slowly see on the guider that the star got brighter. And it's the same effect. It's sped up in, you know, seconds instead of hours.
Yeah, seconds instead of hours here. Yep. Okay.
See, mostly in Stokes U, the middle left plot, you've got an amplitude of 600 parts per million. That's a lot more than at Lick. There's reasons for coating deposition on the secondary mirror of Gemini North that discussion with the observatory. But, you know, the Hippie group also discovered that, you know, this telescope was very strongly polarized. It seems that issue has been addressed. And so we're here to get back on the telescope and measure. But
yay.
The upshot of this paper is it doesn't really matter how polarized your telescope is intrinsically. As long as it's stable, you can calibrate it out.
Yes. Yes. That's a happy message.
A happy message. It's going to be key if, you know, if these 30-meter telescopes ever do polarimetry, because you're really not going to want to spend much time on a bright, you know, 8th magnitude star calibrator. You're going to ideally want to be staring at the target. And so you can take advantage of this field or this Altaz rotation, this parallactic angle variation to calibrate stuff out. And it's actually better than you would get on your calibrator star, because if you've got a strong wavelength dependence to your telescope polarization, you look at a different star that's a different spectral type. Not really calibrating what you think you're calibrating. And so you really do ultimately, theoretically, you know, philosophically want to spend your time on the science target calibrating itself. And there are some ways that you can do that and still be ethical.
Oh, I love that word. I love ethical. Very good.
You're not fooling yourself.
Very nice. Very nice.
So from that, I think point, we go back to probably to figure 15, where we can kind of conclude again, just to, of course, there's a lot of tables. We haven't mentioned at all the tables.
Many tables.
Everything's variable. Everything's variable. That's the option.
Well, so there are some well-behaving stars, a few.
There are a few.
Yeah.
Yeah. So as Olga mentioned, that's how we do it. You know, you have some lab data. We didn't go into, but it's fine. We can, you know, you can read the paper. There's some interesting sources that we look at in the lab. Cavity black bodies really should be unpolarized, and they're not. Linear polarizers are not intrinsically perfect. You can cross them and see weird polarization stuff that happens that must be due to non-ideal physics there, which is kind of cool. I mean,
nice, and get a handle on that.
You know, you take some lab data, you understand when your instrument is right and when your instrument is contaminating, and then you go on Sky and you come up with experiments to try and really determine what's the thing that's going to bump in the night and how to calibrate it. And then you migrate to stars, and then finally you trust your data and you can do these surveys, and weird stuff appears that is intrinsic, and you know, you can look at the interesting physics and you know, say something useful. It's the whole point of exploratory observational science.
Absolutely, like magnetic white dwarfs up there. Very good. Awesome.
Yeah.
Awesome article. Awesome data set too. Very cool. Very, very cool.
I think what is also nice is that in this paper, you know, we compare the results from a meter telescope and with the results of 0.35, so 35 centimeters. This is really cool. And, you know, because the small telescope, they can do the bright stars, but with Polish, we can measure bright stars also on the big telescopes, right?
Yeah, yeah.
And for sure, for many polarimetric measurements, I mean, this is really crucial. I have been observing with the leak now with the double Wollaston, basically photopolarimetric setup. And it was a nightmare for for calibrators. You know, it's so hard to calibrate because the standards that we have, they are very bright. They are 8, 10 Mach, and we really need the dynamic range. We need to have them spread all over the sky. So wherever you are, you know, observing, you always will have someone, some standard star which is nearby your target, so you can calibrate.
Right.
Very
If
nice.
you, yeah.
Okay. Sloane,
Cool.
Aga, I want to thank you so much for walking us through this very awesome decades worth of work on Polish
You're
2.
welcome. Thanks for having us.
Yeah.
Yes. Thank you for the
And,
invitation.
Sure. And you mentioned it a little bit, we sort of jumped a little bit there in the early part. So let me push on that a little bit. So where do you think we go with this technology over, let's say, the next 2 to 5 years? Is it going to be put on different instruments? You mentioned that there is a follow-on to Polish 2, so there won't be a Polish 3, but there will be
Right.
something else. And so just sort of where do we go with this, let's say, over the next 2 to 5 or a decade, if you like?
Right, indeed. So there's still some work to be done with the exoplanet science, especially now that JWST is here, and we need to vet targets properly so that we use JWST time properly. We want to efficiently look at the most important exoplanets. So being able to do some of this on the ground would be helpful to help guide the experimental design. So I'm hoping with Phalanx, which is just hot off the press, newly commissioned at Lick, still working on calibration procedures.
Cool.
That are developed for Polish that can be applied to Phalanx. It's a very similar system. That's hopefully going to be able to get some time on small TAS telescopes and look for exoplanet scattered light.
What's your estimate of the timescale when Phalanx will start producing science level data?
This summer. So
Summer.
we have time.
Nice.
We have time with the Lick 3 meter to look at some of the original exoplanets that were part of our survey with Polish. And we'll do a head-to-head comparison of how well Phalanx does and what are the improvements.
Cool.
Yeah. So hopefully this summer. So working on a paper with the data that didn't go into this calibration database paper to separately publish some exoplanet measurements. So I hope to have that out also. This
And there is a lot of targets that we didn't put in this paper, like debris disk, exoplanets, and also there is a lot of data from the crab pulsar, and we want to publish this, especially in the context of now we have this imaging X-ray polarimetry explorer. That it's already and also the future mission like X-ray polarimeter satellite. So of course, it will be in this multi-messenger approach. We also need to do the multi-wavelength polarimetry measurements for also, compact objects, binary systems,
right?
And the best would be to do it simultaneously or quasi-simultaneously. So this is when the Phalanx will fit just perfect.
Awesome, very cool. Well, I'm really looking forward to seeing polarimetry data and objects. One looks at it from high energy to cooler exoplanets. It'd be really fun to see this develop over the next decade because I think polarization is going to unlock all kinds of interesting physics and ideas that one can explore. Very cool.
Absolutely.
And congratulations on a decade. I got to say it. Congratulations on a decade of Polish.
It was time.
Very cool.
Yeah, congratulations to you, Sloane.
Cheers. Cheers.
Thank you.
Very good. All right, everyone, that will do. And I hope this made your Polarized Astronomy Day just a little bit better, and we will see you on the next one. Bye-bye.
Bye, everybody.
Thank you. Bye.